hold on, Sunflower, hold on. I've been patiently waiting.
Okay,
so
but
to say that they're largely neutral, that's not accurate. You can say that they're slightly harmful, but they are a shuffling of information. Now, we went down this rabbit hole of this magical beneficial mutation, which fine, we can grant you that. But the overall problem that we seem to be dodging is that you're going to, in order to have that one mutation get fixed, and you need it to get fixed, along with that mutation, you're going to have at least 100 other mutations that are going to get fixed along with it by default. So for each, even if we were to grant you one seemingly beneficial mutation per generation, you still have to deal with those 99 that natural selection is not going to remove, because if it does remove them, then there goes your beneficial mutation. So you have a huge problem of mutation accumulation that's taking place. And if you want to, and every time you deal with that and say, well, you know, we have this mechanism that's going to remove these harmful mutations, well, there goes your beneficial mutation.
Yep, I can deal with that. Sure. So what generally happens, and Doc Dino was right that mutation is a variable amount that happens. Sanford was wrong. Sorry, Sanford was wrong when he said that it was only at one rate. That is incorrect. Does that happen at different rates? Now, what happens is that though that beneficial mutation we pass to a number of offspring, as will a random amount of those detrimental mutations, because don't forget the child genome is going to be a random amalgamation of the parents, as well as its own mutations as well, if they do, in sort of point mutations may occur. So what happens is that over a large population, what will happen is the ones with the beneficial mutation will be selected for, because they will be the ones more likely to survive, while the ones with the beneficial mutation and detrimental mutations will probably be removed from that gene pool. What's happening is that even slightly detrimental mutations, they might not be removed from the gene pool. It's once it hits a sort of catastrophic mutational load that organism is then removed. And we see this all the time. We see that, hey, it might have a slight mutation that can still survive, but if they pile up, eventually it will reach a point where that organism and all of its possible descendants will be removed from the gene pool. And that's how it removes those mutations. But it will probably select for the organism with the beneficial mutation and none of the detrimental ones, or the one with the beneficial mutation and just the neutral ones. Because if it does have a detrimental mutation, it will be less likely to survive. If you're talking about an organism that has a mutation that turns off P53, for instance, that instantly that mutation is gone from the gene pool because it's instantly removed. That organism is not going to survive to have children.
Okay, I'm going to address that. So I appreciate those points, Mark. I'm going to get in on this now.
Sure.
This is a good topic, a lot of fun. So that is essentially what is referred to as the mutation count mechanism, where over time enough nearly neutral or low impact mutations will build up in a population that are essentially invisible to selection, but eventually they build up to the point where there's enough genetic sickness in that population that selection can see and remove that organism from the equation. Firstly, I want to point out, I've got it up on screen, it is a well understood and well established principle that the vast majority of mutations are deleterious. This is right from the conventional literature. They also acknowledge that most of these mutations are nearly or effectively neutral. So what that means is they are not big enough in terms of their deleterious effects for selection to see, but they are slightly deleterious. They go on unnoticed. A good illustration would be in the wild, where you have, let's say, a zebra is born with one leg that's too short. That's a big enough mutation for Mother Nature to see. And so that zebra is probably going to be dinner for the lion, while the other zebras might be able to get away. So that mutation's big enough for selection to see. So yes, selection can see the big mutations. Selection can see your rare beneficial mutations. The Lenski experiment has documented that your beneficial mutations are roughly 1 in a million. They're very rare. When they do occur, they're typically reductive, even though the so-called lactase mutation. is due to a mutation in a pre-existing regulatory system. We can get into that if you'd like to later. And so phenotypically, yes, there's a lot of positive effects with these beneficial mutations. But when you look under the hood, when you look at the genotype, mostly we're looking at reductive. We're looking at mutations that are overall functionally compromising to organisms. So the point I want to make to Mark, yes, strong proponents of genetic entropy, whether it's myself or Dr. John Sanford, Chris Root, people who have done a lot of work on this, Dr. Rob Carter, we recognize the fact that there are variations in fitness. Fitness variation exists. But the problem is every single person on this planet, let's take humans, 7 to 8 billion people on the planet. Every single person on the planet is passing on roughly 100 new mutations per person per generation. Most of those being nearly neutral. Selection can't see them, which means they're subject to genetic drift. Okay, so let's, for sake of argument, apply heavy selection to your worst mutant on the planet. Remember, everybody's multiply mutant. Everybody has inherited about 100 mutations from their parents. Your parents inherited about 100 from your grandparents. So everybody on the planet is multiply mutant. So if you were to apply heavy selection and remove 50% of the worst mutants on the planet, let's say 4 billion people, well, is this going to solve the genetic degeneration problem? No, because you're still left with 4 billion people that are more mutant than the generation before it. And so all you can ever do is slow down the genetic degeneration process. You're never going to solve it, because the whole point is that every generation is a little bit worse off or a little bit more mutant than the previous generation. So yes, what Mark is saying, once the mutation load in a population gets so large, selection may be able to see it, but by that point, it's extinction. That entire population, let's say in the case of humans, is essentially removed. So it's never going to solve the problem. Go ahead, and whoever would like to respond.
Sorry, Donny, may I?
Yeah,
could I really quick? So I took a look at this paper because it's on screen, so I figured I might look at it. Maybe just a difference of interpretation, but what they seem to be saying is that the majority of mutations they have found are objectively deleterious, but most of them don't affect the organism in a given environment. They are negative depending on context. Also, what you're talking about of the population just being overloaded by negative mutations, if you could provide me some sources for that, I'd be interested in taking a look at them. But as far as I know, that's not the common consensus for why species go extinct, or at least not the major cause.
What does objectively deleterious mean? Can you just explain that really quick?
They're worse at processing a certain food, but they get so much of it in a lab environment, it doesn't really matter. Stuff like that.
Okay, let's allow Mark to now respond
uninterrupted. That's not an impact? Wait,
yeah,
actually, Sunflower, what we'll do, anybody who wants to get on this specific discussion, we'll go around the room. Okay, so I went, Doc just went, now we'll go Mark Reed. I assume Sam's going to want to go. We can have, whoever. I'm screen shared, so I can't really see everybody who'd want to get involved. But let's go. We'll keep this orderly. So Mark, go ahead. Feel free to respond to whatever you'd like. And then other panelists, make sure you're taking down whether it's mental notes or written notes, and we'll make sure everybody gets the opportunity to respond. Mark, go ahead.
Yeah, and in the conclusions of this paper, it also talks about displaced gamma, where a shifted gamma distribution has the effect of truncating the distribution of mutations below a lower limit. So it's basically saying that once the mutational load gets to a certain point, those mutations and the genetic codes are removed from the gene pool because they're so deleterious at that point. They pile up, and that's what all of the papers say on sort of these deleterious mutations. I talked to a geneticist, and he corrected me on that medicine hasn't sort of stopped genetic selection from happening. What it's done is it's broadened our tolerance for deleterious mutations. Now, you're saying there's no way to solve it, but that simply is not true. If we have medicine that can change, like we can use a CRISPR to change genetics, then we can solve these genetic problems. because once you change the genetic code, then it isn't passed on to the offspring anymore. So
Well,
Donny,
wait.
I'm really sorry, but you're 100% wrong. Like, there is a way to solve it. We might not have the technology yet, but you're sort of saying, hey, there's no way to do it, which I don't think you can make that argument, because you don't know what genetic sort of technology will have in the future. And anybody, no, Sunflower, I'm not waiting. Please, just please let me talk.
Sunflower, you're going to get your chance. Okay, we're going uninterrupted.
You'll get your chance. And plus, like all of the papers that I've read, and what the consensus among geneticists is that once those deleterious mutations pile up, they get selected against. And we have seen this time and time again in labs. Like, for instance, the genetic entropy that said sort of Sanford and Donny and all you guys say should be happening doesn't happen in Drosophila. It doesn't happen in the labs when we've done experiments over multiple generations. There's this genetic decay. Those populations should be wiped out if you are correct. And they're not. They're still going. So it shows that in a practical sense, when you get it in the lab and you actually do these things, it's completely wrong. Completely wrong.
Okay, thank you, Mark. We'll hand it to Sunflower. You've been patient. And then Sam, I know you want to get involved too. So yeah. Sunflower, go ahead. We'll start with you.
Yeah. Sorry to interrupt. I should have been more respectful of uninterrupted stuff. My fault on that. But my main question would be, when you talk to that geneticist, I mean, there's a thing to be said about, like, you know, we have like modern medicine in terms of like diabetes treatment, and maybe other, like we have treatments for other genetic diseases that would have been maybe the end of the genome previously, but that's totally different from CRISPR. I mean, like, was this geneticist saying that like modern medicine, were they equating the fact that genetic mutations are piling up to like CRISPR? Because that's a whole different thing than just modern medicine letting sort of like ill people reproduce. You know, I mean,
he didn't say that, but what I'm saying is, he said that my misunderstanding that modern medicine sort of caused detrimental mutation build-up was erroneous. All it does is increase our tolerance for those mutations, is how he described it.
But we haven't implemented CRISPR yet, as far as I know, to like literally repair.
Guys, I don't want to cross-examine each other. Guys, I'm jumping in. I don't want to cross-examine each other just yet. Uninterrupted responses, and then eventually we'll open it up again for more of a free-for-all, ask each other questions. So, Sunflower, try not to ask a question.
Okay, sorry.
Unless it's like rhetorical or something.
Fair enough.
Mark answer later.
Okay. I won't do a response to that question, but I'll make a brief point that was kind of tangential to all this, but it'll be very brief. Don't worry, and no one has to touch on it if they don't want. I really do think that the scientific method really came into existence and still exists as a means to an end. As in, if you have a overarching moral dogma or purpose or framework in which you can apply the scientific method, it's extremely useful. But once you let people say that, no, this scientific method is now going to replace, whatever purpose or meaning you felt you had as a human, now you can just look into the science and it'll be like peering into a crystal ball, and you'll end up with a reason to keep existing and persisting in life. I think that's really a bastardization of science. I think it exists as a tool, not as an end in of itself. And I think it's dangerous when people start using the scientific method and essentially worshiping it as something that can provide meaning in and of itself. I think it provides a way to be skeptical of other people, to tease out the truth. It will never give you a reason to live and a reason to be excited about life in the future and a reason to be hopeful. And that's why I think it's in the modern era, it's very much being misapplied, and it's not being, it's a tool that's been, sort of co-opted and I think it's like a dangerous weapon in a lot of cases. You wouldn't trust a random like you have to get a license for a gun, but any person on the street can start, wielding science to what they think will be whatever to whatever end they might get to. It could be
Sunflower.
That's it. That's all. Yeah.
I appreciate those points. Let's for now do our best to keep it on the genetic entropy topic. Thank you, Sunflower, for those points. We should probably go, one evolutionist, one creationist, one evolutionist. So, Doc, if there's any points you wanted to make, and then I think we should throw it back to Sam. It doesn't necessarily have to go that way because, I'd like to respond to a couple things from Mark. But to be fair, Doc, let's hand it to you. Feel free to respond to anything you'd like to. Then we'll throw it over to Sam.
Sure, thanks. Just I find genetics interesting, but I honestly, it's not my wheelhouse. So I'm good to just wait until we have some more paleontology or geology questions.
We'll definitely get on to the human paleoanthropology question because there's some points I'd like to make on that. So Sam, over to you, brother.
Yeah. So when you guys, if you go back and you listen, both Doc and Mark acknowledged outright genetic entropy. So Doc says that, they are accumulating, but they're not really affected in the wild. Right. That's the point. There's nothing that's going to remove them. And so when I talked to Mark previously about how do you separate the good ones from the bad ones, he kind of gave an example, but he keeps referring to these things as though that you can remove one thing at a time. It's not. They're whole sets. If you have one beneficial mutation get fixed, then along with that, you've had multiple other ones getting fixed. But notice when Mark was talking about it, on one hand, he fully acknowledged that mutation accumulation is a problem. And he did that when he said, well, we can fix it with CRISPR. Well, wait a minute. Is there a problem that can be fixed, or is there not a problem? If there isn't a problem, then why do you need CRISPR? And if there is a problem, then you've just acknowledged it. And that's the point. The medical journals are full of paper. I've been trying to find this link, and I will, hopefully, when it's my turn again, I'll share my screen. But I mean, there's literally thousands and thousands of genetically inheritable diseases currently in the human population that are not going to be removed by natural selection. Now, the geneticists that Mark talked to about medicine, look, to clear up any confusion, we've heard that before. What the geneticist was trying to say, and you can correct me if I'm wrong, is that medicine has prevented natural selection from working the way that it would if we didn't have medicine, meaning that the medicines are keeping people alive and they are reproducing these mutations into the population, which they previously would not been able to do if there was not medicine. And that's all true, but that totally misses the point. And it acknowledges the point. The point is that there is a problem and there is no solution, and we can put people on medicine to try to help it, but these mutations are accumulating. And if you play it back and you listen to their previous responses, on one hand, they're acknowledging, and I think Doc missed it. But Mark, I'm not saying this deflationary, but he's talking on both sides. On one hand, he's fully acknowledging it, but then on the other hand, he's trying to pretend that somehow it's not a problem. Which is it? And then lastly, when you say that Sanford is wrong, is that an accusation that you're able to defend, or is that just something that you're saying to defend your position, but it's vacuous?
Okay. So you brought up a whole lot there, Sam. So that's
Not
a bit
really.
of a gish gallop. I'll go through all of it.
So
genetic entropy, no, we don't believe in genetic entropy. That's just some sort of an end point to the whole thing. The whole point is that we're saying that these detrimental mutations come to a critical amount and then they're removed from the population. That is not the idea of genetic entropy. That is the build up until some sort of catastrophic event, which we're not saying at all. So no, we don't believe in genetic entropy as far as you say. This whole idea of sets, what you've got to understand is not all mutations are passed to your offspring, that different offspring will have different sets of both beneficial and detrimental mutations. Because you're thinking of it as, well, a detrimental mutation exists, it's passed to all offspring. That isn't necessarily true. Just because someone has sort of a mutation that is sort of maybe diabetes or something, right? So they're susceptible to diabetes. It's not necessarily passed to all of their children because there's two parents involved, not one. We're not cloning them. They're not automatically passed down. So you will have the offspring with different sets of detrimental, neutral, and beneficial mutations. And the ones that have the more beneficial ones and the more neutral ones rather than detrimental are more likely to produce offspring and survive, therefore creating different sets that include more of the beneficial, more of the neutral mutations rather than the detrimental. So you seem to be missing that. I didn't say we could change it with CRISPR now. I said at some point in the future. And that was only because Donny said, hey, there's no solution. And I said, hey, in the future, there might be a solution with CRISPR to take these mutations out. And, you know, sort of what I said with the tolerance is higher. I'm not talking both sides. I'm saying, yes, detrimental mutations do build up, but when they hit a critical point, they're removed. They don't have children. So why we need to use CRISPR if they're removed anyway? Well, I would imagine that someone, say with diabetes, for instance, would be vastly happier having that removed from their genome than actually having it there. So it's not just, hey, we've got to do it because, you know, people have to survive. It's also to improve quality of life and things like that. So I'm not pretending Stanford is wrong. I've got, you know, there are papers where he has used a constant for mutational change. And like I have papers that say that is completely and utterly incorrect. In fact, the person he used their formula to calculate that mutational change rate says that his calculations were wrong. And that was a really, really famous sort of dig at Stanford's work from the person that came up with that formula. So no, I'm not just, you know, sort of making it up. No. But what I would like to know is why wouldn't something with, if these mutational loads build up, why wouldn't an organism with a critical amount of these detrimental mutations, like sunflower described, why wouldn't that be removed from the gene pool? Why would it still continue and have offspring?
All right, yeah, I'm going to address that, and I'm actually shocked that you still do not understand the argument at all. And so I'm going to break it down very simply so the audience can grasp it. Even though I think your worldview is preventing you from grasping the argument. Each generation is accumulating. Hold on. Each generation is accumulating 100, and that's a very conservative number. 100 mutations. Okay, so your parents, 100 mutations from their parents. You picked up an additional 100. So you can't go back in time to that more perfect genome. So moving forward into the future, each generation that survives, reproduces, picks up 100 new mutations. So every child that is born has 100 additional mutations, and that is 100 more in this long line. Now, on an evolutionary timeline, that's ridiculous. You've got millions or billions of harmful mutations. You'd be dead a million times over. On a biblical timeline, we don't have as many mutations. But this is the part that, Mark, you don't get. So when you say, well, once they accumulate to the point, then the organism is going to die. Yes, that's the problem. But the problem is, Mark, if you are born, you have 100 additional mutations. So everyone who survives has 100 additional mutations. And if they reproduce and that child lives, then they are going to have even 100 more. So there is no going back and dealing with it.
Let me jump in real quick, Mark. I know you're making notes.
Yeah, sure. I do want to address that, though.
Yeah, of course. I think I've been patient because I haven't had a chance to respond to the points from like 10 minutes ago. So I'll go, and then we'll hand it back to Mark. And I think this is a good format. So Mark brought up essentially truncation selection. Yes, if you read through these papers, if you read through Kondrashov and his work on why are we not extinct or dead 100 times over, I hear some feedback. So I just want to make sure, check who it is. I think it might be you. Abraham. So I'm just going to mute you real quick. Okay. So you'll notice here from Michael Lynch, world famous population geneticist, he points out that the average newborn contains roughly 100 de novo mutations. So the evolutionary community and all serious population geneticists, they do recognize the fact that the mutation rate is quite high. Now, there is a range from high to really high. So you can have somewhere between 80 new mutations per person per generation up to sometimes 200 new mutations per person per generation. Notice here from Kimura, effectively neutral, but in fact, very slightly deleterious mutants. So he's pointing out that your neutral mutations, your effectively neutral, are basically just very slightly deleterious mutations. They're not big enough, like that example I gave earlier, where you get a zebra that's born with one leg too short. That's a big mutation. He's going to be breakfast, lunch, or dinner for the lion. He's probably not going to survive very long. Okay, a single point mutation can kill somebody. And so there are mutations that selection can see for sure. But the majority of these, roughly 100 new mutations per person per generation, they are effectively neutral or slightly deleterious. Here, Kitely points out it seems unlikely that any mutation is truly neutral in the sense that it has no effect on fitness. All mutations must have some effect, even if that effect is vanishingly small. So those population geneticists in the conventional literature, they have looked to truncation selection, which Mark talked about, so that's good. They've looked to synergistic epistasis. They've looked to various models of mutation count mechanism, which is basically what we've been talking about here, where you've got a population that is accumulating many thousands of nearly neutral deleterious mutations, eventually enough build up in that population that selection can now see the damage, basically. But again, I've pointed out earlier that your damage is population-wide. Every single human being on the planet today has accumulated 100 to 200 new mutations per person per generation. There's a lot of attacks on Dr. John Sanford and his credibility. I would challenge anybody to simply look at his resume, see all of the technical papers he has written, see all the work that he's put out. He's invented the gene gun. He was able to retire at a very young age and basically do full-time research on this because of his excellent work in the field. And he recently spoke at the NIH, National Institute for Health, by no means a young earth creationist organization. And he spoke on human genetic degeneration. And so Doc earlier asked for the evidence of genetic degeneration in humans. Well, that's exactly what he spoke at through the NIH, because there is a concern, especially with working scientists at the NIH, that autism's on the rise, cancers, autoimmune diseases, mutation-related diseases, the environment plays a factor, epigenetics. And so this is recognized. And so they're looking to solutions. CRISPR, you know, with all the many thousands of deleterious mutations pouring into the genome and basically eroding nucleotide sites, you're going to need some really sophisticated CRISPR technology to fix many thousands of nucleotide sites that have been hit with mutations at the same time, because the load is growing and there's really not much of a trade-off. We see what happens with the trade-off with Lenski's experiment. We see shrinking functional genome sizes. And so the last thing I want to say is I appreciate Mark bringing up truncation selection, mutation count mechanism, which some have referred to it as, but these have been looked at. They've been analyzed. This is Dr. John Sanford at the NIH, and he pointed out the various solutions that have been proposed, synergistic epistasis being one, truncation selection. They've been analyzed using sophisticated numerical analyses where they take into account fitness variation, they take into account natural selection, mutations, beneficial mutations, and the result is always the same. Genetic degeneration is inevitable. It hasn't been addressed. And so I'll yield there. Go ahead.
Donny.
Okay.
I would like to move on to a new topic soon, if possible. But real quick,
can I just address what's been said before we do? Because
yeah, I just have a quick question for him.
Oh, if you okay, if you had a quick question,
yeah,
and then we'll throw it to Mark to take as much time as he needs.
There was a
and then, Donny, really quick, don't lose your thought, both of you guys. We haven't had who is it? CR say a word. And Mars Hill, I feel like I owe you an apology. You've been waiting so patiently, and you haven't really kind of got to jump in if you want. But after Dino and Mark goes, maybe you guys want to just say hi really quick, and then.
Well, this is a pretty specialized subject. I got to say,
right.
like, you know,
yeah,
I
don't
blame anybody.
But go ahead. I think Don.
Right. So
yeah. Go ahead.
Okay, really quick, Donnie. On the topic of, say, cancer as an example, do you think there are any other possibilities for why we're seeing more cases of cancer other than genetic degeneration? Could there be other causes?
Great question. Absolutely. Dr. John Sanford addresses that in his lecture at the NIH. I highly recommend checking it out. I've got it uploaded on my channel. It's got, I don't know, 10, 12,000 views. Definitely check it out. And so he goes over the fact that cancer rates, they're skyrocketing 1 in 3. And a lot of it has to do with mutations. A lot of it has the mutation accumulation, basically relaxed selection as well on humans, you know, and environment. We've got a lot in the environment with the foods, radiation, chemicals, carcinogens. And so there's a lot at play. And so there's environment related entropy as well, for sure.
Thank you. I just wanted to make the point that there is more than one cause for what we are seeing.
It's a combination, many factors.
It's a combination, and there's a lot of arguing within the scientific community, because there always is, about what the bigger causes are. So some might agree with you with the genetic degeneration. Depending on how you define it, that could be happening. But there's other causes too. That's all. Mark, your go.
Okay, so just first on what Sam said, like the 100 mutations, like what you'll notice is, and maybe you saw it on that paper, it says on average there is 100. And also what sort of Sam and Donny aren't telling you is that it's split into coding and non-coding regions, where the mutation might not actually do anything because that genome is not actually expressed in the organism. So the whole idea that it has to lead to this degeneration, it doesn't happen in the labs. And the whole point is that, you know, Sam's sort of saying, oh, it's 100 and then they get 100 and they get no, that's not how it works. Some of the children will have more, some will have less, some will have no, like very, very few detrimental mutations or even no detrimental mutations, because the vast majority are neutral. And yes, Donny's correct when he says, hey, nothing is completely neutral. Yes, it's all very spectrum driven. Some things are nearly so far to neutral it's almost, you know, absolutely nothing. Some are neutral because the environment doesn't affect it. Put them in a different environment and it may do. So yes, but most of them are neutral. So the whole idea that they have to get detrimental mutations is just reading 100 and sort of saying, well, each one gets 100 is very misleading. And I think that has to be pointed out. And I also want to point out that Stanford, and I'm not going to, like, he's done really good work. The gene gun was genius. He's done fantastic work, but that he can't get genetic entropy published. And there's a reason why. It's because the consensus of geneticists don't agree with him. And he lacks, he has a problem with the way that he's calculating genetic mutation rates. And that is in a fixed linear fashion at a certain constant. And it is just not constant. It is affected by all kinds of things that occurs. Even diet and what environment an organism is in can affect mutation rates, how much sun they're exposed. There's a multitude of things that can affect mutation rates. But if Sanford was correct in that certain generations of mutations, and we can measure them in Drosophila, which is fruit flies, they have a very, very short lifespan. If he was correct, those colonies would be wiped out, and they are still going to this day. Unfortunately, genetic entropy is not correct because when we've tested it in the lab, it has been falsified. That is the end of that. And unless Stanford can come out with a paper that gets peer reviewed by the people doing work in these labs with organisms with short lifespans that show genetics to be the way that he says it is, I don't know what to tell you. I can't, he just doesn't really have anything to say. This truncating that we're talking about, it does definitely occur. And, I'm glad that Donny sort of acknowledges it occurs, but it still means that these build-up of sort of detrimental mutations will be removed from the population. And the whole idea that just because it's a large number, 100, it doesn't say whether it's encoding or non-coding reasons. So even though that mutation might happen, it may not actually be a region that is expressed at all. So it may not have anything to do with it. Epigenetics may mean that it never comes into play, that, maybe it's detrimental, but it never is actually comes into play at all. So it is not.
May I make a request?
Sure.
Sorry. Just I appreciate you helping, Mark, but just maybe we should try to keep responses to 30 seconds or shorter.
Well,
just
I mean, I'm trying to go through everything.
I know there's a lot, but
all right. Well, then,
sorry. Yeah. Just it's hard to respond to every point.
Doc, if you wanted to, okay, you know what, Mark, I appreciate that. Let's throw it to Sam and let's try and, me and Doc at the same time, we can time if you want. And let's try and limit it now to, let's say, minute responses as we move slowly towards. I think this has been great. We could probably talk about this all day.
Well, I do acknowledge that Doc's field isn't genetic, so maybe we should shift to his, what he wanted, because it was his debate. I do.
Okay, Sam, let me start. I'll take a minute, and then Sam, you take a minute, then we'll throw it back to Mark. I know he'll have some points to make, and then Doc will slowly start shifting to some of the points you made in the debate on human evolution. And so let me start my timer. I'll go a minute, which means I probably won't be able to address everything, but I will address as much as I can. So here's at least one paper. There's been many in terms of Mendel's accountant, the sophisticated program that basically looks at mutation distribution, looks at selection, beneficial mutations, truncation selection, and determines if mutation accumulation is resolved, if it can be resolved. So here's one paper, and you look at an old virus, patterns of mutation accumulation. So basically, this is in the secular literature, so you can look at it here. And Rob Carter and John Sanford published, basically assuming that mutation accumulation does result in genetic sickness. They looked at the H1N1, and what they discovered that due to mutation accumulation and randomization in the genome, basically of this virus, we had a virus that was red hot in terms of being a pandemic, and it went to a whimper and to an extinction event in something like 90 years due to mutation accumulation. The last thing I want to point out is the fact that they've looked in the lab, Lenski's experiment, for example, these E. coli bacteria, we have generations after generations of E. coli. And what they've discovered is due to mutation accumulation, they have actually shrunk in functional genome sizes. Many pre-existing systems have been destroyed. They've lost a lot of genes for short-term adaptive purposes, but it's actually long-term degeneration. This is well understood in bacteria. It's called reductive evolution, where bacteria will adapt to different environments, but they'll do it by basically losing systems, breaking down pre-existing genes, but overall it results in genetic degeneration. So yeah, we have observed it in the lab, but the concept of genetic entropy was written with long-lived mammals in mind, elephants, humans, and that's where we see these high mutation rates. We see generation times of 20 to 30 years, rather than with bacteria, it's every 15 minutes. And so populations can recover quicker in bacteria. So I'll wrap it up there.
Donny, brother, can you share my screen? Sure. So what I'm going to do, I'm going to take you guys to the most relevant laboratory that we have. And so this here is from medlineplus.gov/genetic/condition. And this is the National Library of Medicine at the NIH. And there are literally thousands. So here you can see they're all alphabetized. And so as I scroll down, I think it's better if we can just visually see like what Mark is saying. This is what he's denying. And so earlier in the stream, we stated, Donny showed very clearly that genetic decay is very well established. Talked about how Dr. John Sanford spoke at the NIH. I'm still on A, by the way. But Mark says he's been refuted, but it's just been a vacuous statement. And then he says, well, he has to provide papers to prove him wrong, but that's not how it works, Mark. The one making the claim, they have the burden of proof. And so just saying that somebody doesn't like his numbers, that's hardly a refute at all. So here you go. On an evolutionary timeline, on any timeline you want to say, look, we'll go to another random one. Here's like the G's. And we can just continue to scroll through all of these. Now, this makes sense on a biblical timeline. And again, Mark, I feel like every time you respond, you're not comprehending that it's each new generation picks up 100 new mutations. That's 100 more. They don't just disappear. The only way that those things go away is if the organism dies. But all of the other organisms on Earth, they still have all of those accumulated mutations. And lastly, I want to say, it would be better for you, if you want us to take you seriously, to exercise a little bit more terminological exactitude. Because on one hand, you're saying that they're neutral, but you just acknowledge that they're not actually neutral. Then stop calling them neutral. They're not neutral. Don't call them neutral. They're either neutral or they're not. You've already acknowledged that they're not. Stop calling them neutral. Okay? And so, yeah, that's it. Like, I'll put the link in the chat. You can click on any one of these things. It'll open it up and give you specifically an analysis of what it is. Here is what I'm showing. And there's thousands of them. Mark, where's natural selection? Where's the hero? That's all.
Yeah, so I'd like to respond to that if I could.
Please.
Because I think that's a bit inflammatory to sort of say that what I said was vacuous and I had no idea and that exactitude. Yeah. They're called neutral because they have no effect on the success or detriment of the
I just showed you that.
That's generally why we call them neutral. So this whole idea of the 100 mutations they last in the environment, I think that you're misunderstanding what these mutations are. Like, they're not the same mutations, and they're not sort of, it's not like every single animal gets exactly the same mutations kind of thing. I'm not sure what you're thinking, but they hang around in the environment. No, they don't. You came, the organism dies. Yes, the organism dies. And a lot of these things that you're pointing to, they basically can be managed by modern medicine. So as I said earlier, I'm not sure if my exactitude actually sort of passed you by, but we have a higher tolerance for diseases that ordinarily would have removed organisms from the gene pool in the past. So basically you're pointing to this, basically you're pointing to this and basically you're pointing to this and basically saying that, if I could talk, please talk. Okay. Could I talk?
You're just contradicting yourself. I'm just pointing it out. Go ahead. Which is it? They're accumulating or they're not? We have medicine or we don't? Like, which is it? You're talking out of both sides of your face. You don't even realize it. You're contradicting yourself every
Sam, I think you're just not understanding what he's saying.
No, I showed. I understand. Donny's giving you papers. I just showed you. Like, we understand it. Like, one of us does.
You're pointing to a large amount of diseases that we can now tolerate because of a greater medicine. And those aren't necessarily like diabetes, as I pointed out with a specific example. They're not necessarily passed down to any offspring because they're sometimes in the non-coding regions. They're sometimes not expressed. Sometimes they mutate further. There's a whole bunch of things that happens that doesn't necessarily mean that they're passed on. A lot of the times they are, sure. But once the mutational load becomes so detrimental, as you said, the organism dies. Where's my hero? Natural selection? It's not my hero because we've got medicine to try and increase the tolerance range of what, like, because in the past, someone with diabetes just would have died, but they don't anymore. but we can use medicine to increase that tolerance. It doesn't mean that genetic entropy is going on.
I'm going to respond real quick, Sam.
But
Mark, in all due respect, you're still not getting it. It's the nearly neutral mutations. It's the nearly neutral mutations that are the problem, not the big mutations that kill somebody, not the big mutation in the wild that results in a zebra being born with 3 legs instead of 4, and therefore it's the first to die. No, it's about those nearly neutral mutations that accumulate population-wide. So you keep saying that eventually they'll accumulate to the point where Mother Nature can see the damage. Yeah, the damage is population-wide. So what you get is extinction. That's not going to help the case for you. Every single human being on the planet is multiply mutant. And so what type of selection can you present us with today, Mark, that can actually remove these nearly neutral mutations as they're accumulating before it results in population-wide genetic sickness? Go ahead.
Yeah, so when it reaches a certain critical point, that person will no longer be able to interbreed.
What do you mean that person? Survive. Every person has a critical load.
I just
so is selection going to remove every person at the same time?
I gave you a list of thousands of genetically inheritable diseases. Thousands of them. It's like you don't even look at it. Like,
well, Sam, let me just cross-examine them real quick.
Because diseases kill people, Sam.
This is insane. Mark,
does diseases kill people, Mark, Sam?
This is crazy.
The diseases kill people, Sam? Did
you not just see what I showed you?
Well, it's a question. Ridiculous. Do diseases kill people, Sam? Do they kill people?
Yeah, but that doesn't mean that kills them before they reproduce.
Sometimes
those are
it does,
inheritable. Right? Inheritable.
Sometimes it does, and when
diseases get passed on, Mark? Mark, do inheritable diseases get passed on? Do those thousands of inheritable diseases get passed on?
Sometimes they don't. Sometimes they do. Yes, they will do. However, when there is comorbidities, when multiple detrimental mutations build up, usually they will not get to interbreed before they die, and they will remove that specific line from the gene code, and you still haven't addressed why these populations of fruit flies are not having this happen to them. They get the same mutation load.
Well, you know what? It probably is happening in fruit. Let me talk. It probably is happening in fruit flies. I haven't specifically looked at that one, but I've looked in bacteria. Lenski's long-term evolutionary experiment. That's the longest running macro evolutionary experiment to date. And he's documented the fact that, firstly, there's a new paper that came out in 2021 where a lot of these beneficial mutations that were observed, they're actually now being lost. We see that his bacterial species are shrinking in functional genome sizes, but I don't want to get too far off the point. The point is, it's the accumulation of your low impact, your nearly neutral mutation. So it's not necessarily about the diseases. It's not necessarily about the disease that manifests, that prevents reproduction. No, it's the ones that go on unnoticed. And these are only subject to genetic drift. And so if they're subject to genetic drift, what happens? They spread throughout the population. So Mark, I agree with you. Eventually, the damage is going to be so catastrophic that the entire population is now experiencing universal genetic sickness. So is selection going to remove every single person from the equation? Is that your solution?
No, it's not causing sickness, because if you realize that what you said was nearly neutral is ones that would have a detriment in a certain environment, but you're not in that environment. Generally, humans have changed the environment. So those ones that, you know, if we were out in the wild and had, say, a temperature tolerance issue, we don't have that problem anymore. We've removed that problem. So these kinds of neutral mutations that, yeah, you could categorize them as detrimental, and Doc made that point that it's only detrimental in certain environments. They are no longer the detriments that are going to take us out of the gene pool, and that's what increasing tolerance means. We no longer have the problem that if you have low blood pressure, you're going to not be able to hunt or something like that. So these have absolutely been... Our tolerance for them is so much higher and so much better that, yeah, even if they build up in the population, it's not a problem. And, you know, it's not guaranteed that they will be passed down, because if you get somebody with that mutation breed with somebody without the mutation, it's not guaranteed that that's going to be passed along.
Let me respond real quick. So again, the nearly neutral mutations, I wouldn't necessarily call them detrimental. I'd call a mutation that kills somebody before they can reproduce, or a mutation in the zygote that basically doesn't result in the birth of that being. Or, you know, again, the example of the zebra in the wild that's born with one leg too short, where it doesn't last very long. It doesn't even survive a year or two because the lion is going to choose that zebra for dinner. And so whether it's in the wild, whether it's in humans, it's not about your detrimental mutations, your mutations that are big enough for selection to see, and therefore there's no reproduction. It's not about your rare beneficial mutations that may or may not be on the genotype reductive. It's about that accumulating load due to the low impact mutations that population geneticists refer to. Recognize there's an issue. That's the whole point of invoking truncation selection, synergistic epistasis, mutation count mechanism. So the point is, when a population reaches a point where their genetic load is so high that selection can see it, it's either extinction or a certain part of the population doesn't reproduce and is removed from the equation. But what that means is every other individual is still mutant. And so it only ever slows down the problem. But what I want to point out here before you respond is you can find paper after paper from Dr. John Sanford and other researchers on this. Some are published in the conventional peer-reviewed literature, others in creationist journals. There's a good mix for you to look at. But here's just some that you can go through. And in these papers, they look at synergistic epistasis. They look at truncation selection. They look at various models of mutation count mechanism. This paper is the one I was pointing to earlier. So if you click it, you can go read it on the H1N1. This was published in the peer-reviewed literature. And it's always the same outcome. Genetic degeneration is inevitable. Yes, there are circumstances where it can be slowed, but never have we seen an example where it can be completely stopped. Go ahead.
Okay. Well, the whole idea is you're using mutation as if it's always bad, like we're all mutants. And yes, that's essentially true. Everything's been a mutant since the dawn of time, essentially. Everything's always mutating. It doesn't necessarily mean everything's headed for a catastrophic state. And this is what the Lenski labs, this is what the Drosophila, this is what all the experiments carry out. Now, you're talking about a virus, which is a bit of a different thing than animals. I haven't looked into that. I certainly will look into it and see if there's any sort of genetic entropy they're sort of saying there, or whether the virus is succumbing to an inability to propagate itself. Because a quick skim, and I must admit this was just a skim, it sort of suggested that it moved away from its host populations and didn't go there, which, you know, tons and tons of extinct creatures have showed us that, yeah, extinctions do happen. And just because you're saying, hey, that would mean extinction for humans if this is happening, or if that's happening, maybe it would. It doesn't disprove evolution. There's been 99% of all species have gone extinct. So what does that show? I mean, I don't get your point here, really, that evolution isn't true because genetics can't make it true. I don't really understand what you're trying to get at.
Well, basically, the argument, I'll say this, the argument can be boiled down to the fact that if mutation accumulation essentially puts shelf lives on genomes today and moving forward, Mark, then species won't be able to persist for millions of years into the future. Therefore, going into the past, species cannot persist of millions of years into the past. And so it puts shelf lives on genomes today and shelf lives on genomes in the past.
Yeah, Stanford's done a lot of good work, but that sort of constant mutation rate, I mean, everybody knows it's not constant.
Yeah, Mendel's he would agree it's not constant. Well, Mark, you keep saying that he says mutation rates.
Mendel's accountant does use a constant mutation rate.
You can do variation in it. You can do a variation in mutation rates.
But when you're applying it to populations, you have to apply the same rate, right?
You can do a mutation rate of 1, and
Yes.
it's still too much per species. 1 mutation per generations. So for sake of argument, you can run a simulation of 1 mutation. Because,
I don't think that's true.
No, but what is true? Because mutation accumulation and genetic entropy, Mark, it's about every generation being worse off than the previous generation. So even if the mutation rate was 10 per generation, that's still more than the previous.
Does Mendel's accountant take into account the beneficial mutations?
Yes. You can set parameters, and it's been done, where you have super beneficial mutations, or you have, rather than 1 in a million, you could have more frequent beneficial mutations. And all you're going to get...
I really think in order to believe Sanford, I think he should get something peer reviewed as, his model of genetic entropy.
He has.
I think that's what he... Okay, can you cite that?
Mendel's accountant is peer reviewed.
That's just your bias speaking.
So
that's a fallacy of an unargued philosophical bias. That's all you're doing. You have no reason to dismiss his work. Donny, can you share my screen one more time?
Really quick, can Mars please go? Mars has to go soon, and he's been very patient. He's been here for like an hour.
Show something really quick. I have articles, Mark. Humans are getting dumber. The human IQ is on a decline. We've got articles that most mutations are harmful. I think I've beat that one up. This one here, I think you might be interested because it's in Australia. We've got humans are losing fertility. Autism is on the rise. Gene loss and broken genes in humans
is a problem with
on
autism?
the rise. But this one is cancer, and this is in Australia. Look at the title of that. This isn't some creationist site, by the way.
Look,
It talks about the rate of childhood cancer in Australia is increased by 1.2% per year between 2005 and 2015.
Redefine, you got to remember.
And is in it. Hold on, we're going one at a time, and it's expected to go further, 7% over the next 20 years. So, these are all the results on your. Here's the question that you asked. On your model, Mark, this mechanism that creates beneficial mutations, also, even if we grant those, it also creates an accumulation of deleterious mutations. Now, I've shown you thousands of examples, independent examples. You said I didn't do that. That list that I put in chat from the NIH, there is thousands. I think there's 6,000 or 7,000 independent single examples of a genetic inheritable disease that you can click on any single one of those, and that's going to be one independent line.
Redefine. Remember the way they're defining.
Bubbles. Let me finish. Let me finish my thought. So just really quick, all I'm saying is I have now given you thousands of independent lines, and you've not given us any beneficial mutation. You keep saying they exist, but we're the ones that are providing the literature and the sources and the references, and you're literally hand waving it away, pretending like we're not even sharing the stuff, and then going on and talking without addressing anything.
You gotta let the people know why he's doing that. You got to let the people know why he's doing that. His definition of fitness. If all the retards in the world start reproducing, that is still fitness by his definition. So it will still be
Godzilla, bubblegum. Come on, come on, man.
So you have to point that out.
You've been here for 30 seconds and you've made an unnecessary comment. Just keep it sophisticated, like we've been doing.
What's a better word for the mentally disabled? The mentally disabled,
I'll agree that
reproducing.
Wait, hold on. I don't think we don't.
I would like to respond to what Sam said because he threw out a few things.
That'd be fantastic.
Yeah. So if you want beneficial,
don't just hand wave it.
Sure. If you want beneficial mutations, there's HIV resistance, which I brought up to Donny before. In the case of people having HIV mutating that retrovirus into a beneficial function, I've got lactose intolerance, which Dr. Dino brought up. lactose tolerance, rather than intolerance, what is it? Trichromatic vision is a beneficial mutation. It certainly can help people, or women rather, because it's women's. Excuse me, bubblegum. It certainly does help women in, recognizing color and fashion industry and things like that. So that can be a beneficial mutation as well and assist in their reproductive success. So that is something that is also a beneficial mutation. So there are definitely a few out there. I think I brought up the case of some people in a car accident I can't remember the state, it was in the US. They actually found to have a genetic marker which had made them have heavier bones, more density. They were sort of better off when in accidents or crushes or things like that. But unfortunately, they had trouble swimming because they were actually denser. So there's all these examples of beneficial mutations.
This is
now,
false.
your whole thing about, hang on, I got to address what Sam has said. Okay, everything that he said, because I want to get through everything. The whole point about you bringing up children with cancer, children die of cancer. That selects children that survive. So thank you for bringing up a perfect example of how detrimental mutations are removed from the population before breeding age by bringing up deadly leukemia.
No,
well
Mark,
done.
It was the argument wasn't that children don't die from cancer. It was that the rate of children in the population is increasing. I have another article from, I like the medical journals because that just really flies right in the face of evolution with literally, again, not to be redundant, thousands of examples. So you gave me a small handful. One of those with the lactose, that's already been addressed as being a deleterious, sickle cell trait. That's another one. That's a disease that has a beneficial effect, but it's not something that you would want. But I granted you them. Here's the thing, Mark, for like the free thinkers, right? The one who really wants to freely think about this. And I wish that's you, Mark. Like, I hope that's you. But I realize it might not be, right? But anyone else who's listening, if evolution is true, there should be millions of examples of beneficial mutations, because that is the mechanism.
Let me address a couple of these real quick, if you don't mind.
Wait, can I go? I got here first.
I'm going to go first because I've got my notes here. I don't want to forget. There's some background noise there, typing, I think. And then Mars will allow you to ask your question too. I'll point out to the panel and then also the audience, after the 2-hour mark, which is more formal, it kind of becomes a free-for-all. And so you kind of got to jump in there and, ask to be part of the uninterrupted portions and stuff. And so we will wrap up this portion soon. We're all passionate here, Sam, myself, Mark. So, but Mars, we're going to make sure you get the question. So anyways, lactase and HIV resistance. HIV resistance is probably one of the better examples of a so-called beneficial mutation. Firstly, I like to point out that you're going to need more than 1 or 2 or even 100 truly beneficial mutations that on the genotypic level is not reductive at all, because I find that 99.9% of the time we're discussing beneficial mutations and defining what a beneficial mutation is. We're defining it based on the phenotypic effects, the physical features of the organism, or what's going on, outwardly, basically. Like sickle cell anemia, those with sickle cell anemia, they're actually resistant to malaria. They're not going to get malaria. But what's going on the genotype or under the hood? Typically, it's due to the knocking out of pre-existing systems. And so one example, HIV resistance. That's an interesting one. And so there's a number of people on the planet that are resistant to HIV, and they actually have a mutation. I can hear someone typing. They have a mutation in the gene that makes the CCR5 mutation. Okay. And they no longer have it on their T cell. This means the HIV virus, therefore, in those people cannot bind to that T cell, because viruses, in order to bind, they basically need a key to bind, to get in, to infect. And so in this case, when you look on the genotype, it's actually the result of a pre-existing protein being knocked out. So a couple things. This mutation doesn't tell us where these genes came from in the first place. Overall, it's reductive and functionally compromising because you're knocking out pre-existing systems. The lactase mutation, same thing. It's a pre-existing regulatory system being damaged. We can get into that, but for sake of time, I won't. Because the point is, you're going to need, hundreds of truly beneficial mutations that are not reductive in any way to counterbalance the damage being done through the influx of so many low-impact mutations pouring in generation after generation. And I'll yield there. Mark, to be fair, we'll hand it to you. Once Mark's done speaking, we'll throw it to Mars.